So hello, welcome to today's class, a strange Friday lecture where I'm actually lecturing Friday and not just doing practice problems. I mean, I say it's strange, but I've done it now 50% of the time because I did this for chapter 1 also, but it's not going to happen again all semester. The rest of the semester would be lecture Monday, lecture Wednesday, practice problems on Friday. Today though, because this chapter is longer, I'm going to lecture today. Practice problems for this Practice problems for this chapter will be Monday of next week. Wednesday of next week, I'm going to go through last semester's exam, and as I go through it, kind of give hints and tips for this semester's exam. And Friday will be this semester's exam, covering once again chapters 1 through 4. At the end of today's lecture, I'm going to talk about the exam in a bit more detail, what exactly you should be ready for. But really, as I said, a lot more detail that will come Wednesday of next week. Any questions about the exam or anything like that before I get started? Okay, so we've been talking about forces. F equals ma. That's the basis of this entire chapter. In fact, so far, it's the only equation of this chapter. But what we're going to talk about today and spend all day talking about is a special force we need to include when we say F equals ma. That special force, really I should clean my glasses before we start, is friction. You see, so far we've just kind of ignored friction. We're just like, yeah, someone pushes a thing, it moves. But we can't always assume friction is zero. We're going to continue to assume air resistance is always zero because that just makes life easier. But we need to talk about what happens when we actually do have friction. That if I take, I can see it again. If I take a block and slide it down a ramp, well, there's friction when it goes down the ramp. Earlier, we talked about how it went down the ramp. We could talk about the acceleration going down in case of that call, but that was with the wheels. With the ramp, there should be some friction. And so we're going to finally work that out. Now, friction comes in two flavors, kinetic and static. Let's start with kinetic friction. Kinetic friction is the force of friction anytime an object is moving. There was a kinetic friction between the cat and the ground in that horrible, horrible GIF. When this thing slides down, that's kinetic friction. If I put it here, there is no kinetic friction there. That is no kinetic friction. But right here, there, where it goes, when it starts going, that's kinetic friction. It's any time you have two objects moving or rubbing against each other, you have kinetic friction. Friction traditionally uses a lowercase f instead of a capital F, just to keep it separate. And kinetic friction would be F sub k, lowercase f sub k, k for kinetic. And anytime you have kinetic friction, the direction of the friction will be opposing the movement. If you pose something to the right, friction is to the left. If you pose something to the left, friction is to the right. And the magnitude of kinetic friction goes by mu of k times n. Well, mu of k, you know what, I'm going to change the way this slide's set up slightly. Mu of k is the coefficient of kinetic friction. I don't know why that one's so small. I'll fix it some other time. Mu of k is the coefficient of kinetic friction, and n is the normal force, which we had spoken about 2 classes ago. And so yeah, anytime you're moving, kinetic friction, mu of kn. So coefficient of friction times the normal force. Static friction is the friction of something not moving. If something is stationary, it has static friction. Going back to my video here, when I put the block there, that is static friction. And yeah, that is held in place because of static friction. Gravity wants it to go down the ramp. Static friction keeps it from going down the ramp. When I start lifting this, still static, still static, still static. Nope, now it's kinetic. And you have static friction anytime something isn't moving. Now, static friction is a little more complicated. It has a varying value. To show you what I mean, there we go. That's what I want. Let's just get rid of that. Zoom out. And let me grab something heavy. I should have thought of this ahead. No, those are all light. Those are all... You know what? Scanlan will work. Okay. Let's say I go and try to push this thing to the side. If I push it, I'll push it from the top. If I push it this way, I'm applying a force this way. If I just barely touch it and push it, I'm applying a small force. It's not moving. It has no acceleration. So that means the sum of forces must be zero, must be canceled out. And I can say that it's friction that keeps it from moving. If I push heavier and it still doesn't move, if I push heavier and it still doesn't move, that means the sum of the forces is still zero. That means that the static friction must have gone up also. And that's the general idea. Static friction is whatever value it has to be to keep something from moving. That will be low if you push lightly, but harder if you push heavier, as long as the thing isn't moving. Scanlan was not heavy enough. And that's the general idea. Static friction, you know what? This would have worked good. My pens. Yeah, because I can just lightly tap this, or I can push harder. But you can't really tell how hard I'm pushing online anyways. Thing is, static friction does have a maximum value. That static friction can be anything it needs to be, where static friction be F sub S, until it's that max. That's why it's less than or equal to mu of Sn is the equation here, where the maximum value is the coefficient of static friction times the normal force. And what it is if I take this and start pushing on it, I must have something with more friction that I could use. Really, I should plan this stuff out ahead better. You know what? My water bottle is pretty heavy. It's full. And it's way too tall. Okay. That works. So if I start pushing on this, if I push lightly, it has static friction to bounce. When I push harder and harder and harder, what's going to happen is static friction will get bigger and bigger and bigger until I push hard enough to move it. And at that point, that means I went above the maximum value of static friction. But the maximum value of static friction is F of S sub M. But it can be anything leading up to that. As I look around for more things that have more friction. Any questions though? Now, let's say I take something, put it down, and start pushing on it. What's a good base? Right? So I'm going to take something, sit it down. There has to be, you know what? This Muppet is pretty heavy. And yes, okay. What's going to happen if I take this, just put it here and start pushing on it? Initially, there'll be no friction. And if I just slowly increase how hard I push, I go from 0 newtons to like 10 newtons to 20 newtons to 30 newtons to 40 newtons. I'm not going to go that high, but you get the idea. What's going to happen is as I push it, friction will change. What will happen is that when I push this thing, static friction will be however hard I push it. That if I push him with 10 newtons, if he doesn't start moving, static friction will be 10 newtons. If I then switch to pushing him with 20 newtons and he doesn't move, static friction will now be 20 newtons. And this will continue until I hit my maximum value of static friction. Once I hit my maximum static friction, it'll start moving. Once it starts moving, I no longer have static friction. If it moves, I have kinetic friction. But here's an interesting thing about static and kinetic friction. The maximum value of static friction is always greater than the value of kinetic friction. If you were to graph the force of friction versus the applied force, that if I just say I steadily push harder and harder and harder, what is the force of friction? It would look like this. That the force of friction would just go up until it hit that max value. The max value be mu of Sn. Once it starts moving, the force of friction would drop because the value of kinetic friction, the coefficient of kinetic friction is always less than the coefficient of static friction. Where mu of S and mu of K are those two coefficients combined. And so you can figure out, and so once something is moving, it'll always move easier than it took to make it move. Does that make sense? Now,
Can you say it one more time? I'm sorry.
so if because I put that thing away for no reason, let's use my pens again. So if I want to figure the maximum value of static friction, mu of Sn, is always going to be greater than mu of Kn. That the amount of force it takes to make something start to move will always be greater than the force required to keep it moving once it's moving. And if you ever try to push a heavy object, this might sound familiar, right? You start to push the thing, and once it starts going, it kind of goes easier. That is real. That is what happens. It is harder to make something start to move than keep it moving. Does that make sense? Did that explain it better?
It does. Does the formula say this though, or kind of does common sense say this?
Well, common sense kind of is, but not traditionally in the formula. Where that would show up in the formula, if anywhere, is because the maximum value of static friction is mu of Sn, and kinetic friction is mu of Kn. And I'm just telling you, mu of S is always bigger than mu of K.
Okay. Okay. All right. I got it.
And I'll go in 2 slides. I'll talk about mu of K and mu of S in even more detail.
Okay.
Now, the reason for this. Oh, before I get into the reason for this, if you ever want to find the minimum force required to make something move, which is going to happen sometimes, I'll say problems like, how much force do you need to apply to get the thing to start moving? The minimum force to make something start moving, whenever you want to solve for it, will always be when static friction is a maximum and the acceleration is 0. Because when static friction is a max and acceleration is 0, that's when you're on the cusp of moving. That is the very, 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 very limit. And so I'm going to sometimes get problems say, what's the minimum force required to push this object? Solve for f of s is max and acceleration is 0 to do that. Okay, so what friction is, why friction is that no objects are perfectly smooth. All objects on the microscopic level and some on the macroscopic level are jagged. Oops, didn't want to do that. Wanted it to do this. And that if you zoom in on an object, it'll always look like it has like teeth and be, jagged. What happens is if you take 2 objects and push them up against each other, these teeth might kind of line up. That if I put this styrofoam block on top of the other one, I can get it that it doesn't really want to move because the teeth kind of get stuck on each other. That's what static friction is. Static friction is when the 2 things are stopped on top of each other and it's stuck in there. Now, if you get an object moving, what's going to happen when the object's moving is it's going to kind of skip across the tops. And that's kinetic friction. And this is also why the maximum value of static friction is always greater than the maximum value of kinetic friction. Because with static friction, it's stuck in the teeth. But once you begin moving, it can kind of skip across the tops. Kind of the idea of like, on a bumpy road, go a little fast, kind of skip some of the holes. And so static friction will go is when you settle down in. And kinetic friction, the top pieces are just going tick, 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 and skipping across the top without settling. This is also the basis of lubrication. Like if you have machinery and you put some lubrication for oil, what it is just fills the teeth with a liquid. So then instead of the teeth connecting, they're floating on a bed of liquid between each other. Other interesting thing about coefficient of frictions, coefficient of static friction and the coefficient of kinetic friction don't have a set value for material. I can't say like this is static friction for wood, this is static friction for metal. The coefficient of frictions goes by pairs of materials because it's how well the teeth line up. The styrofoam block I'm playing with, or I was playing with, this styrofoam block lines up real well with my surface. But if I switch it to a different styrofoam block with a different shape, it's not going to get nearly as stuck. It's going to move easier. Coefficient of frictions exist for pairs of materials. And that if you need the coefficient of friction, which will always be, you don't need to memorize these. I'll either give them to you, or it's going to be what you're solving in the problem. But the coefficient of frictions will be for steel on steel, or aluminum on steel, or copper on steel, and so on. It'll always be for pairs of materials. And once again, mu of s will always be bigger than mu of k. Now, crazy thing about these is if we look at the equations, we said, I'll do kinetic friction for now, that f of k equals mu of k n. Well, f of k is a force, so f of k will be in newtons. And n is a force, so n will be in newtons. What this means is the coefficient of frictions are unitless, and they always have no units. But once again, static friction can be anything up to the maximum, where the maximum is mu of Sn, and kinetic friction is always mu of Kn. Any questions though? Let's do some problems. The first one, which I lovingly titled, Why One Should Never Plug in Numbers Until the Last Step. It says, a steel box is sliding on a steel floor in the positive x direction. What is the acceleration due to friction? I said steel on steel, but here's with wood on table. This is the problem. I got this thing moving, and it slids to a stop. And I say when I let go, not counting when I'm touching it, but while this thing is moving and sliding to a stop, what's the acceleration? Okay? So here's my problem. I got this box, it slides, and it comes to a stop. For some reason, off the end. I should really make that end longer. If I want to solve for this, is that x? Sorry, my line for x is like, I think it's not flat, it's up at an angle. I'll have to fix that sometime. If I'm going to solve this, I'm going to start the same way I always do, with a free body diagram. So, what forces are acting on my steel block as it slides to rest? Anyone?
Gravity, normal force, friction, and I think that's it.
Yep, gravity, normal force, friction, and we think that's it. And that's correct. When this thing is sliding, that's the only forces acting on it. When I was pushing on that block, if I go back to the video I had, there was some. But while it's sliding, gravity holds it down, the normal force keeps it up, and friction is what slows it down. Now we know F equals ma. And I can say in this problem that there is acceleration in x. It's slowing down. But there's no acceleration in y. Acceleration in y would mean that as it's sliding across, it's either going up or down. And it can't go down because it's on a surface, and it's not going up because it's not going up. Going up would mean that someone went and like flipped the table as it slid. And so those would be my equations. So I'm going to make some space by getting rid of my title. And I'll say, okay, I can use this to make my problems. Now in friction problems, friction depends on the normal force. Any friction problem, you're always going to have to do the sum of forces in y just to get the normal force. Unless the normal force is in x. That happens sometimes. We're going to see that in chapter 7 when we revisit this idea. And so I'll say in y, my equation in y is always up minus down. Up, I have n. Down, I have mg. And my acceleration in y is 0. So in y, my equation is n minus mg equals 0. Or n equals mg. Now in x, it's right minus left. But there's nothing to the right. So it's nothing minus f of k. It's nothing minus whatever is to the right. And so what I'll say is, it's just negative f of k equals ma. Negative because it's to the left. Now, a lot of people like to plug in numbers right away. If you tried to, you'd say, okay, we can get the normal force. Normal force is mg. Let's plug in, get n. But I don't know m. I can't get n without m. But I can keep solving. You see, f of k, we've already said today, f of k is the force of kinetic friction. And the force of kinetic friction is mu of kn. Okay, this comes up a lot, so I'm going to stress this right now. The force of friction and the coefficient of friction is not the same. And people often interchange them. The force of kinetic friction is mu of Kn. The force of kinetic friction is the coefficient of kinetic friction times the normal force. And I just said above that in this case, the normal force is mg. This allows me to divide both sides by m and say my acceleration is the coefficient of kinetic friction times g. And so as long as I know the coefficient of kinetic friction, I know the acceleration because I know g. Now, I did say it was a steel box on a steel floor. So I can just go back to that table I had and say steel on steel, there's my values. And I'll say the acceleration is the coefficient of kinetic friction for steel on steel times g. And get a value. Any questions though? Okay. Let's do a more complicated one. This next one is not an old exam problem just because it has too many steps. There's a part A, B, and C, and that's just too long for me to put in an exam. If I did it on an exam, I'd probably only do 2 of the steps, and I've done ones like this that have only some of these. I've done basically the equivalent of number C as its own problem, and I've done the equivalent of A as its own problem. I just wouldn't ask for all 3 of these on them. And what it says is Mario, as in Super Mario, is standing on a spinning platform. He has a mass of 89 kilograms. And I kind of have a GIF of this below. Spinning platform that keeps going. The coefficient of static friction between his boots and the ramp is 0.876, and the coefficient of kinetic friction is 0.753. What is the force of static friction between Mario and the ramp when it makes a 20-degree slope? Now, this is assuming he's not sliding hill, because I asked for static friction, so you can make that assumption. So that'd be like, the GIF doesn't really stop. Let me do this. So that would be the equivalent of this when it's just sitting there. That while it's just sitting there, what is the coefficient of friction? I then ask, at what angle does it begin to slide down for B? And for C, I say, screw it, it's at some high angle. What's the acceleration? We clear where we're at? So let's look at what we know. We know the mass of Mario. We know the coefficient of frictions. And that's all the knowns that are going to be constant. I do know 20 degrees in A and 45 degrees in B, but let's do each part separately. So we're going to come back to those. If I want to solve this, I'm going to start the same way I always do, a free body diagram. And I'm going to say what forces are acting on Mario. So you guys, what forces are acting on Mario?
Normal, gravity, and friction.
Yep. Gravity, normal, and friction. I'm doing a different order just because PowerPoint, I can't switch it on the order wheel fly. Now this one, it says we're looking for static friction, so we can assume it's static friction. And we'll say gravity is straight down. Normal is perpendicular to the ramp, and friction is going to be along the attempted movement. So it'll just be straight up the ramp. But this is a ramp problem. In a ramp, you want to use a tilted coordinate system. We're going to say X is down the ramp and Y is perpendicular to the ramp, just like we talked about on Wednesday. And if we use a tilted coordinate system, where instead of XY, we're going to do XY. If I do that, gravity is not in X or Y, and gravity will need to break into components. And for any ramp, the X component of gravity is mg sine theta, the Y component is mg cosine theta. Once again, ramps are backwards from the normal. Now we're looking for force of static friction. So once again, we're going to assume he's not moving. If he's not moving, he has no acceleration. And we'll say F equals ma. But if he's not moving, A is 0. And just like always, really, this is two equations. One in X, one in Y. But I have a free body diagram. I can make my equations. So one of you guys, what's my equation in X?
mg sine of theta minus f of f sub s equals 0.
Yep. How about in Y?
89 kilograms times gravity, so 9.81 times sine of 20.
No, I said how. I don't know Y equation. What's my?
Oh, y would be n minus mg times cosine of theta.
Correct. And we can use this to solve. See, we said, what is the force of static friction? Now, we don't know if he's at a max value. Static friction can be whatever the hell it wants to be. So I'll just take my X equation and solve it. And say the force of static friction is just mg sine theta. Or mg sine theta. That's the force of static friction. I'm not going to solve my Y equation because I don't happen to need it here. That's part A. That's when he's just stationary. Part B says at what angle do I raise to that he starts sliding down? What is that angle? For part B, my free body diagram doesn't actually change. It's still all the same forces. We're just finding the moment he begins to slide. And if you want to find the moment he begins to slide, that will be when static friction is a maximum. See, since f of s is less than or equal to mu of Sn, that means it's going to be a maximum when f of s is mu of Sn. And we'll just say his acceleration is 0. And so I'll say, okay, I get equation x and y. But once again, the free body diagram didn't change. X equation changed. X equation didn't change. Y equation didn't change. But now I'm looking for the angle. Now I'm looking for theta. But static friction, once again, is at a maximum. That is what it means to find the moment he begins to spin when static friction is a maximum, when f of s is mu of Sn. I can add mu of Sn to both sides though. And I'm going to do something kind of weird here. I'm going to kind of do stuff in an order that wouldn't immediately be predictable. I wouldn't normally put this problem on an exam because the algebra here, you'd kind of have to think of some trig identities to really do easily. It's something I'll do in class because it has weird trig identities. But for now, just take my word for this. I'll divide both sides by n. Now, when you're dealing with friction, once again, you're normally going to need your y equation to solve for n. So look at my y equation, say n minus mg cosine theta equals 0. And adding mg cosine theta to both sides, I get this equation. And I'm just going to take that n and say this n goes in right to, oh, I missed, right to that n right there. And so mu of s is mg sine theta over mg cosine theta. This allows me to cancel out my m's and my g's. And that mu of s is the sine theta over cosine theta. Now this is kind of interesting. That means that mass doesn't matter. Mario standing on the ramp, he'll start sliding at a set angle. Luigi on the ramp, he'll slide at the same angle. Just his shoe without him in it on the ramp, it'll slide at the exact same angle. All that matters is the coefficient of friction. Also, this is the trig identity. I don't know if you guys would know off the top of your head, but the sine of theta divided by the cosine theta is always the tangent of theta. Just so you know. Sine over cosine is tangent. And if we want to solve for theta, I'll just take the inverse tangent of both sides. And say the angle here slide at will just be the inverse tangent of mu of s.
Well, That was a lot.
You think you could?
Do it again? No, I couldn't do that
No,
again.
I could do it again. Do what?
What
Dab
time?
it.
What time?
I'll just get down there at like 3:10, 3:05, I'd say probably.
I
What's
gotta
the-
run. I gotta run before I work out, and I gotta work out at 3:45.
Oh, is this not to me? I think this
Oh.
is not to me.
Probably not, unless you really wanted me to.
Well, how far you run?
Okay, I think that conversation wasn't to me. If it was, you can unmute yourself, but it sounded like it was about something else, so I just muted you. Sorry. If it is to me, unmute yourself and ask a question. Good.
I have a question. So could you have taken the inverse sine of the mu static times n divided by mg?
I could have. It would have got a little ugly because I'd still have n, and I would need to solve for n with mg cosine theta, and I couldn't solve for n because I don't know theta.
Oh, okay. Okay.
But that will give me the answer. It's 41.2 degrees. This reminds me there was something I forgot to say. Mistake I made. When I was first showing you the coefficient of friction, I forgot to say a very small thing. Coefficient of frictions are always less than 1. A coefficient of friction can never be greater than 1. I forgot to say that before, and I apologize. That is the largest coefficient of friction can ever be, is 1. And if that wasn't true, you might run into some issues with the sine theta and cosine theta because of the nature of. Oh, sorry. Yeah, you might run into issues with this equation because the natures of sine and cosine and tangent. But coefficient of frictions can never be greater than 1. I'm sorry, I forgot to say that. Any other questions though? So this is at 41 degrees he begins the slide. And part C says, okay, he slides at 41 degrees. What's his stupid thing resizing? What's his acceleration at 45 degrees? If he slides at 41, what happens when we put him up there? If we go past 41 degrees and go to 45 degrees, what that's going to mean is he's going to be sliding down the ramp. If he's sliding down the ramp, that means he no longer has any static friction, and he has kinetic friction. But my free body diagram doesn't really change. The only change to my free body diagram is where I had mu of s, it becomes mu of k. That's it. And I now have acceleration in x. I still have no acceleration in y because he's just moving down the ramp. He's not moving away from the ramp or into the ramp. And for my equations, it's still right minus left. It's still mg sine theta minus f of k just equals ma now. And for y, it's still up minus down n minus mg cosine theta. And if I want to solve for the acceleration, I can say, okay, we have kinetic friction. Unlike static, kinetic friction has a set value. If I know kinetic friction, I know kinetic friction. But I'm going to need the normal force. If I want to solve for the normal force, I go down to my y equation, like n minus mg cosine theta equals 0. So therefore, n equals mg cosine theta, just like we did the last two bits. I'll take that n and shove it into my x for n. Divide everything by m. And note, my m's cancel out. I told you before, I've done this as a problem on the exam before, where it was just this part C, no parts A or B. And when I did, I didn't give the mass. And it drives people crazy that I don't give the mass. If I don't give it to them, it's because you don't need it. It cancels out. But here I can then plug in my numbers and solve.
Just to double check, you said it was kind of unique that mass didn't matter. Was that right?
No, it's not unique the mass is. It's just that it's everywhere, so it cancels out. I do a lot of problems when mass cancels out. Cancel out the first problem we did and part C of this one. This problem was more unique that I gave a mass when you didn't need it.
Oh, okay.
But it was needed for Pod A. That's why I gave him mass. Plus, Nintendo has officially stated what Mario's mass is, so it's kind of a known quantity. Not that anyone would know without looking it up, but I spent a lot of time looking up shit like that for test problems. But yeah, no, you needed the mass for Pod A is the only reason I gave it. Questions though? Let's do one more without a ramp. And this problem is this. I'm going to take something and pull it at an angle. But while pulling at an angle, have it move flat across the table. Except because I want to keep it interesting, and this is an old exam problem, it's about Krampus. So, in Germanic folklore, Krampus is a horned figure described as a half goat, half demon, who during Christmas season takes bad children or children who misbehave, throws them in a sack, and drags them down to hell. It's a thing. If you ever want to see some crazy shit, watch like some legit Germany Krampus celebrations. It's a thing. There's weird people in costumes and fire, and it's scary but kind of awesome. Yay, German pride. So let's say Krampus has a bag of children, and his bag of children has a mass of 60 kilograms. And Krampus pulls the bag of children with a force of 400 newtons at an angle of 35 degrees. What is the coefficient of kinetic friction if Krampus is moving at a constant velocity? Now, if I want to solve for that, what's forces? How to solve a force problem never changes. You start with a free body diagram. Why are you not clicking? There you go. And so I can say what forces are acting on my bag of children. Only the most cheerful things in physics class. And what I can say is gravity pulls it down. He's pulling it, so there's a tension. It's coming across the ground, so there's friction. And it's on the ground, so there's a normal. I also said he's moving at constant velocity, so the acceleration is 0. Now, this is not a ramp, so I could use my standard coordinate system. I'm going to say x is to the right and y is up. But for my standard coordinate system, I can see tension is up and to the right. It's not up, it's not to the right, it's up and to the right. And so my tension, I need to break into components. I'm going to say, fuck that noise with t, let's make it t of x and t of y. Where t of x is to the right and t of y is up. And I can solve for t of x and t of y by saying t of x is t cosine theta and t of y is t sine theta. Or 400 cosine 35 and 400 sine of 35. To get my values of t of x and t of y. Once I get that, I'm going to ignore these numbers. I don't need those. I just needed to get these numbers. Any questions so far? So with my new free body diagram, I can solve. There's F equals ma. But constant velocity, so acceleration is 0. And really, this is two equations, one in x, one in y. And I'll make my equations. So, someone, what's my equation in x? No one? What's pointing to the right?
T sub x minus f sub k equals 0.
Yep, that's my x equation. How about my y?
T sub y plus n minus mg equals 0.
Yep, because it's up minus down. T of y is up, n is up, mg is down. Now, this is kinetic friction because it's moving. And I can say the coefficient of the force of kinetic friction, I misspoke, the force of kinetic friction is the coefficient of kinetic friction times n. And I'll take that and shove it in for f of k in my x equation. I can then add mu of kn to both sides and divide both sides by n. And so the value of mu of k, what I'm looking for is t of x over n. Thing is, I don't know what n is. So I'll use my y equation to solve for n. I'll go back down to my y equation, say t of y plus n minus mg equals 0. And I will add mg to both sides. I will subtract ty from both sides. And say n is mg minus ty. That's my value for n. That's what I shove up in there. And this is my equation. I'm going to say this now. How to solve a force problem, why this is the hardest chapter, probably of the entire class, is because there's no set process other than make a free body diagram and make your equation x and y. How you handle those, how you do the algebra, how you rearrange them will be different for every situation. You're going to have to figure it out using your abilities in math. But at this point, I can plug in numbers and get a value. Now, I did say that the largest this could ever be is 1. So this is super bumpy road. This is really, 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 really high. But, you know, we're dragging a sack of children down to hell for being bad. So I think we have other things to worry about than how rough the ride is. Seriously, Krampus is really kind of crazy. I made a movie a few years back about Krampus. It's like half comedy, half horror. Questions about this problem?
Can you remind us how it would have been different if there was an acceleration and it wasn't constant velocity?
If there was an acceleration, it would probably be an x. There probably would be no acceleration in y, because if there's acceleration in y, he's lifting it off the ground. And so what would happen is this would not be 0. This would be ma. So this would be ma. And this would be ma. To here, this would be mu of kn plus ma equals t. And that would make, yeah, a whole nother term show up. I skipped this step just because I can't fit it, but does that make sense?
Yes, yep.
Any other questions about this or chapter 4 in general? I got like 7 minutes left and I have a plan for that 7 minutes, but any questions? This is the end of chapter 4. So any questions here? Okay. Because I have 7 minutes left, I actually would do the exam in a little more detail. So once again, practice problems Monday, review for the exam on Wednesday, exam is Friday. Make sure you have a calculator for the exam. It is open notes. You can have anything you want in front of you. I recommend having an equation sheet so you don't need to look up various things. You can have whatever you want in front of you, though. It will be 4 questions long. The first problem will be free fall. The second problem will be projectile motion. The third problem will be forces without friction, maybe with a ramp, maybe not. The fourth problem will be forces with friction, maybe with a ramp, maybe not. I've already written the exam. I've taken the exam. I've written the solutions for the exam. I have a time limit that I don't give an exam unless I could do it in a certain time period, and I'm well under it. Should be pretty fair. So, knowing that's what's going to be on it, this is what you should make sure you should know. Unit conversions will get mixed in. Know your kinematics. But really, as I said, it's going to be with free fall. So for free fall, we just change our x's to y's and make our a's negative g's. Projectile motion is these equations right here. Though you will have to break vectors into components. And break vectors into components, that is these equations. Or go the other way. This might be for forces, this might be for velocities. They work either way. And for forces, we got F equals ma and friction. So, any questions about the exam before I end today's class? I'm just playing with the tape measure.
Are those all of the equations that'll be needed most likely?
Yeah, I mean, how to do a unit conversion, which I wrote unit conversions. And, keep in mind that these right here, that this could be V naught X equals V naught cosine theta. This could be T of X equals T cosine theta. Or the fact that these might switch for a ramp. I didn't write them out for a ramp because I said if theta is measured from horizontal. So if it's a ramp, remember to make them backwards. That's the general idea.
All right, word.
Okay. If there's no questions, I will end here. Have a good weekend, and I'll see you Monday where we'll do example problems. Have a good day.
Thank you.